My name is Michael Fitzgerald, the architect of the space elevator in service to the International Space Elevator Consortium. I'm also a vice president of Galactic Harbour Association, and we intend to build this thing in the next 15 years. Our vision is shown on the first chart, but let me get into the engineering background and the path we covered to get where we are now. I'm going to start with a quick description of certain aspects of what we went through, and they are part of architecture engineering. And if you haven't heard about that, send me a note and I'll be glad to tell you all about it. But let me make a couple of points about what architecture engineering has meant to us in the context of figuring out what a space elevator transportation system really is. On the left-hand side is a list of things everybody has done in the system engineering of a system, ending up with built-in test equipment down there at number 9. But in architecture engineering, we take a slightly more open-minded and modern approach. And I won't go through all these, but let me mention 2 of them, which were critical to our maturation from a technology solution to an engineering solution. First of all, we recognized that the parts of the space elevator were just fundamentally incompatible with each other. To solve that problem, we recognized that we needed interfaces between these incompatible parts, and the interfaces are armed with artificial intelligence based on data collected in an extensive testing program. Let me give you a little more information. This is sort of the rule that Dr. Swan and I put together, and they say they must be integrable or integrated together. There's nothing more incompatible than something sitting in the middle of the Pacific, for example, and the apex, which is out there in outer space. And Dr. Swan and I realized we needed to get those things to be integrated or we'd not have mission success. That's one important aspect of what we have overcome in the last, 7 or 8 years. The other thing we did to satisfy the first requirement is to recognize that the interfaces between these pieces, and I'll explain the pieces here in a minute, is that we had 2 fundamental functions. The interfaces obviously have to connect, but most importantly, those connections have a process which make the parts compatible with each other in an operational sense. So this make compatible function is unique to what we did. And remember, the interfaces are intelligence. They learn from the moments before and forecast the moments coming. Now, why can I say that? Well, let's talk about that for a minute. We put together a tech maturity plan, and at the end of that plan, we were going to achieve readiness. That's what we do. But definitely, that's what ISEC has been doing since it was born, and certainly what it's been doing for the last 10 or 12 years. The technology plan is as showed, and this is almost in any system and architecture engineering 101 story, but let's examine it in terms of exactly what the ISEC engineers or the ISEC scientists have been doing. We completed the first box. I want you to have that in mind. We have determined that tech is not only feasible, but is valid for performance in the space elevator. Now we are ready to enter the second box, which says, I know how to build it with the technology that has now been validated. So the engineering version of the first box is now underway. In the first box, what we did is we documented the technology as best we could find it and understand it by reading everybody from the Russian scientists that imagined this 100+ years ago to the most recent arguments about how to build a space elevator. The technology discussions were just humongous. They're all over the place. And we looked at, as far as we know, we looked at all of them. Based on that, some of them were more mature than the others. So we assessed whether or not what others were saying and what ISEC had determined whether that was a ready level of technology. So what we did is going through all that we determined that if engineering approach could be validated and then verified, we can, and given success criteria for those verifications, we should be able to proceed. And that's what we did in phase 1. We weren't perfect, but we were hardworking engineers and scientists, and we think we've gotten there. In phase 2, a little more detail here, and I've documented it thoroughly, but once again, it's a direct quote from pages in our report of the space elevator architecture and the roadmaps. For your references, you can read through these words. If you want more, we can tell you how to get the report. But most importantly is industry is beginning to get involved, and that's necessary. And secondly, at the end of this phase 2, the performance of the envisioned concept is predictable and baseline. That's number 6. That basically is the pass-fail criteria for the third blue box, which we figure is 4 or 5 years hence. We determined that we can build it. The tech maturity is there. The schedule is not crazy. We can add and subtract things with an on-ramp criteria, and we can set the standard. Very proud of that. It was great work. It's underway and needs to move faster. Now, some of you may be more comfortable with the notion seen on the left in green, technology, engineering, design, etc. What we have done at the ISEC and the Galactic Harbour Associates is sever that slightly differently in the face of the recognition that we need intelligence interfaces. So the list of testing that's cited on the right-hand side is essential for phase 2. We have to get Pathfinder started in almost all segments, but especially in the Tether segment. We have to see if we can make a tether, connect up, etc. That's why we reconstructed the normal engineering steps on the left to the 8 steps on the right. We call them the sequences. Sounds mysterious. It isn't. It's straightforward. Now, let me make one thing clear. It's very important that all of the listeners here see that the space elevator is really the space elevator transportation system and the space elevator enterprise system. Everything we're talking about today is how we're building the main channel in the Galactic Harbour. And we're talking about the 6 segments, 6 subsystems, however you want to think of that. The businesses are coming. This is a little bit of we will build it and they will come. But believe me, they've already started showing up. But we are building the transportation system, and that's what we're talking about. For those of you that don't understand the notion of a main channel, here's a picture of Long Beach Harbor and Los Angeles Harbor together. And that red line I've inserted is the main channel. This is a crazy place, these 2 harbors. I'm sure you've seen a truck on the highway and it's got a container on it. This complex, using the main channel to park their container ships, have been moving nearly 1 million containers a month. That's an incredible number. So we know that we have a lot to learn from the transportation industry because we are building a transportation story, the main channel. This is the floating ops platform for the Earthport. It is indeed in the, quote, middle of the Pacific Ocean. It was point selected because of the weather and other sensible considerations. It is where the cargo that's going to go up be handled here at the Earthport. Let me show you this more clearly. This is engineering quality of what we intend to build. You can see the living quarters on the light colored deck. The gray levels are the operations center. And down here, clean rooms preparing cargo to go up. The cargo is received on the right, processed on the left, and then put on a small craft that you see in the foreground. Then it goes up the tether. Now, to give you another insight as to what our engineering status is right now, here is an engineering drawing that we were working on just 2 weeks ago, and we are going through the detailed engineering of how to load a standard container into those little squares that you see in the climber. The climber sits there in the gray, the containers are in the lighter gray. The tether is going to be discussed thoroughly later, but the point is that this is the essence. This is the last hurdle from the technology work that we have been doing. Secondly, I want you to realize that what we envision is a region geosynchronous that's huge. The gray cylinder is basically the size of Southern California, and think of it being serviced, if you will, by 2 rail lines going through it, receiving cargo from the Earth and sending cargo or other things up to the apex anchor. And the apex anchor is shown here. It too is a region. One of the reasons it's a region is because this is where interplanetary missions will come and go. And I believe Dr. Swan has cited this as the manner in which we can receive and deliver cargo. That's it. That's the story. The argument has been presented in 11 or 12 studies listed here. We have each of them available to any of you. The top one is still in process, by the way, and 3 other international studies that are listed at the bottom. This is not just bravado. This is serious technology and engineering evaluation work. Thank you. This is the transportation story of the 21st century, and I hope you all come and join us. If you have any questions, send them in.